Thank you all for attending and welcome to the 41st episode of Covalent Academy, where we're hoping to dive into the power of ToF-SIMS. Our experts are excited to share their knowledge on this topic with you. I'll be handing off to our experts in just a moment, but before that, we have a few housekeeping items for you. Tatyana, next slide, if you please. Everybody is muted at the moment, but we do encourage you to post questions in the Q&A chat, which is located at the bottom of your screen. After the webinar, we will share the recording and slides, as well as the Q&A submissions and answers.
So I'll give a quick intro to covalent metrology before we start. So we offer a range of analytical services, and we're really here to help you accelerate your projects and your materials innovation through supporting characterization, imaging, failure analysis, and testing, as well as consulting in those areas. We have more than 50 modern instruments in our lab. Many of them are cloud connected for remote operation, and we're really flexible in how we work. We can stream the analysis through Teams, through live sessions, or you can even come and work on the instruments with us in our lab. And we have many strong partnerships with instrument vendors. Next slide. And yeah, we won't go too much into this. Here's a quick summary of all our capabilities across many different areas of microscopy, materials or electrical testing, and failure analysis. So we're going to be focusing here specifically in some chemical analysis in the surface analysis area and talking about ToF-SIMS.
And with that, it's my pleasure to introduce today's speakers. We have Dr. Tatyana Kravchuk and Dr. Lyle Gordon. Tatyana has over 20 years of experience in surface science with specific focuses in batteries and semiconductors. Lyle also has extensive experience in ToF-SIMS, specifically within atom probe tomography. As you can see, both have a fair amount of experience and they're very excited to share their knowledge with you today. Tatyana, I'll let you take it away. Tatyana, I think you might be muted.
Yeah, thank you. Thank you for the introduction. To start, I would like to take you on a brief journey through the history of ToF-SIMS, how it all began and how it has evolved over time. The story starts in the early 20th century, when the foundation of mass spectrometry was first developed. From the 1910s to the 1940s, scientists led the grand work for the powerful analytical technique, then described the secondary ion emission and developed spectrometry. A major breakthrough came in the late 40s, the invention of first time-of-flight analyzer and the description of secondary ion spectroscopy. Then in the 1970s, we saw another big leap. This is when the first commercial ToF-SIMS was built by Benninghoven at the University of Münster. Around this time, major industry players like Cameca and Kratos Analytical emerged, shaping the field. And now, fast forward to today, and we are witnessing incredible advancement, higher lateral resolution, improved sensitivity and depth profiling, and cutting-edge developments like AI-driven data analysis and automated sample handling. Current use of SIMS is divided mostly between semiconductor industry and material science research, with some interest also in life science and geoscience. Typical examples of SIMS application are surface analysis and contamination detection for semiconductor wafers, optical lenses, and biomedical devices. Depth profiling in thin films and coatings to evaluate the composition and distribution of the materials in multi-layer films for electronics, photovoltaics, and protective coatings. Understanding the chemical composition and degradation mechanism of polymers, adhesives, and coatings. Mapping the distribution of isotopes in geological samples. Analyzing drug distribution in tissue samples. investigating electrode surface composition, degradation products, and ion distribution in battery materials. Now let me go over the basic principles of time-of-flight secondary ion mass spectrometry, or ToF-SIMS for short. This is a powerful analytical technique that combines two key ideas, which you can see on this slide. First, let's look on the left side. The SIMS principle. Imagine we have a sample and we heat it with high energy ions, which we call primary ions. These ions have thousands of electron volts of energy, and then they hit the surface and knock off tiny particles. It's like throwing a ball into the sandbox. You will see some grains of sand fly up. Now some of these ejected particles become charged, and we call them secondary ions. These are ones we analyze. However, not everything that gets knocked off is useful. Some particles stay neutral, and some are electrons. As you can see on the diagram, we don't use VOSI for our measurements. Now, once we have our secondary ions, we need to figure out what they are. That's where the ToF analyzer comes in. The idea behind this is simple. If you give ions of different masses the same energy, they will move at different speeds. Lighter ions will travel faster and heavier ones will move slower. So we use an electrostatic field to accelerate all the ions to the same energy level. Then let them travel through the analyzer. As they move forward, the detector. We measure how long each ion takes to arrive. This is their time of flight. By knowing this time, we can calculate their mass with incredible precision. SIMS measurements can be performed in two different modes, static and dynamic. Let's take a look at the key differences between them. On the left, we have static SIMS. This method uses a very low ion dose, less than 10 to the 12 power atoms per square centimeter. Because of this, it's great for ultra-surface analysis. Typically, we use primary ions like gold, bismuth, or gallium. For mass analysis, we rely on time-of-flight spectrometer, which gives us both elemental and molecular information. Now let's compare that to dynamic SIMS. This method uses a much higher ion dose, hundreds of times more than static SIMS. It's especially useful when we need to remove material and perform depth profiling. For this, we usually use oxygen or cesium as the primary ions. Unlike static SIMS, the analysis here is done using quadrupole or magnetic sector mass spectrometers. Now let's explore the key instrumentational components. The time-of-flight mass analyzer is shown in component A. The bismuth cluster ion gun, which serves as a primary source, is a component B. Component C shows a spatter gun capable of generating both cesium and oxygen ions. This versatility allows us to optimize the analysis depending on whether we are looking for positive or negative secondary ions. The load lock chamber and the sample manipulator arm, marked as a component D, enable us to introduce samples without breaking the ultra-high vacuum. Two additional features which enhance ToF-SIMS analytical capabilities are flat gun to compensate for charging and 5-axis stage. This combination of components allows to perform high-resolution surface analysis with excellent mass resolution and spatial precision. We have seen on the previous slide that ToF-SIMS is equipped with two ion guns. Let's elaborate on advantages of this design. As was mentioned before, for spatter ion beam, ions like cesium, oxygen, or argon are usually used, while bismuth ions are used as an analysis ion beam. The key advantage is that each beam can be optimized independently for its specific purpose. The spatter beam operates at low energy but high current, which allows it to efficiently remove layers of the sample material while maintaining good depth resolution. Meanwhile, the analysis beam uses high energy but low current, which provides excellent lateral resolution for analyzing the surface with minimum damage to the sample. It is common to use a spatial crater spatter crater 3 times larger than analysis area to avoid measuring the edges. The timing diagram on the right shows how the Z-beams work in sequence, with the extraction of secondary ions occurring after each beam pulse. The tree diagram at the top illustrates the process. First, the spatter ion gun removes material, then the primary ion gun pulses, and finally the secondary ions are extracted for analysis. This dual beam approach offers better control and more precise measurements than single beam technique. Let's now focus on what can be measured by ToF-SIMS. Surface spectra can be measured with 0.005 atomic mass units mass resolution, with ppm sensitivity enabling precise molecular characterization of upper surface. Surface imaging delivers 0.3 micron lateral resolution with simultaneous mass resolved chemical mapping across fields of view, which may vary from microns to centimeters. Depth profiling combines 1 nanometer depth resolution with sputter rates up to 10 micrometer per hour, while maintaining sensitivity. Finally, 3D reconstruction integrates these capabilities, enabling comprehensive volumetric chemical analysis with full retrospective capabilities. Keeping these properties in mind, let's see the place of ToF-SIMS within other surface-sensitive techniques. Please, Lyle.
So you might be wondering when you would choose ToF-SIMS over other surface analysis techniques. So we won't go into all the details, all the advantages and disadvantages here, but this talk's recorded, so you can always come back and look at all this information. So as Tatyana said, ToF-SIMS has a really unique combination of high spatial, high depth resolution, as well as very high sensitivity to trace impurities or contamination in the parts per billion level. So talk a little bit about when you might choose ToF-SIMS versus some of the other surface science techniques that we offer at Covalent. So if you don't need the high spatial resolution, then XPS can be a really good choice. It gives you simpler quantification, where most of the time you don't need standards to get accurate quantification, and you also get chemical information like oxidation state, which can be really valuable for understanding different impurities. And then SEM EDS can provide more bulk information to the micron length scale, and it can offer really quick and simple mapping, as well as giving you complementary SEM information of the microstructure of the sample. And then another really unique technique that compares as well is ISS, otherwise known as low energy ion scattering. This enables even higher depth resolution, but effectively no lateral resolution. It's a few millimeters. But what this allows you to do is characterize just the topmost layer of a sample. And this is really useful for very thin ALD films where you're trying to see if they're conformal. And so hopefully that gives you an understanding of when you need ToF-SIMS. Usually the answer is when you need high resolution. And then you can look at all these notes to see the specific advantages. And I'll now give it back to Tatyana.
I would like to highlight the essential capabilities of ToF-SIMS through the measurement results from different areas. I will start from this fascinating example of high-resolution surface contamination analysis. On the left, you can see a color-coded overlay map showing a distribution of 3 different chemical species across a 15 by 15 millimeter area of silicon wafer surface. As you can understand, this is a fingerprint. The map shows sodium in red, which comes from the salt residue from finger contact, silicon in green from the underlying silicon wafer, and organosilicon compound in blue, which is assigned to PDMS, a common silicon-based contaminant. The spectra on the right, they are extracted from the measurement during post-analysis. The area of analysis may be as small as few square microns. We can see the incredible molecular details this technique provides. The top green bordered spectrum shows various silicon peaks, including isotopes. Zoom in on 29 atomic mass units. Region demonstrates the impressive mass resolution. Peaks are separated by 0.01 atomic mass unit. That's particularly powerful about this analysis is that it combines large-scale mapping with detailed chemical identification, allowing us to not just measure the spectra of contamination, but also create a chemical map. This kind of information is crucial for quality control in semiconductor manufacturing. In this example, we use time-of-flight SIMS to visualize calcium and sodium contamination on aluminum surface and demonstrate techniques visualization capabilities. On the left, we see depth profile, which tracks the signal of calcium, sodium, and aluminum ions as we go deeper into the sample. For 2D visualization, we use a color-coded overlay map, red for calcium, green for aluminum, and blue for sodium. This shows how these elements are spread across the surface. If we measure this sample, the EDS, we would see something like similar results. Next, the XZ slice of the depth profile of calcium gives us a side view, how the calcium is distributed vertically, while line scan gives relative numbers to the colors in the image. The 3D reconstruction takes our analysis further, creating a 350 nanometer deep volumetric visualization. The color coding is the same as before. This three-dimensional mapping allows us to understand how the surface contamination penetrates in the sample. ToF-SIMS provides both visual and quantitative data, allowing for detailed multidimensional analysis of contamination. Let's continue exploring depth profiling, this time focusing on depth resolution using aluminum gallium arsenide superlattice. On the left, depth profile shows clear repeating layers of aluminum, gallium, and indium. The 2D overlay confirms the same pattern, highlighting the precise separation of elements. That makes this result so impressive is the high depth resolution. We can map elements at the nanoscale with incredible accuracy. Notice how alternating layers stay well defined across the entire depth of the analysis. On the right, the 3D rendering focused on aluminum distribution, adding another layer of information. This shows how ToF-SIMS provides detailed subsurface chemical analysis while keeping excellent depth resolution. Such precision is crucial for semiconductor manufacturing, while measuring accuracy makes a big difference in quality control. This slide highlights how ToF-SIMS helps us analyze semiconductor contacts formation, specifically between aluminum zinc oxide and gallium nitride. To give you some context, I would like to start from the sample description. 100 nanometer of aluminum zinc oxide, or as we call it, azo, was deposited on magnesium-doped gallium nitride layer with alumina as a substrate. Then the 30 nanometer gold layer was added on the top to improve the conductivity. Now let's walk through the key findings. On the left, you can see the IV curves, which show how the contact properties evolve with temperature. Moving to the depth profiles, we compare the sample before in black and after heating in red. The left graph shows that aluminum and zinc ions from the azo layer diffused into gallium nitride after heating. The right graph shows the opposite, gallium and magnesium ions from gallium nitride diffused into aluminum zinc oxide layer. And why is this important? Because this mutual diffusion is key to forming a reliable electrical contact. Even though ToF-SIMS give us semi-quantitative data in this case, the trends we see here are trustworthy and meaningful. The next example is a typical task for ToF-SIMS, comparison between a good and a bad sample. Let's start with the structure we analyzed. It consists 30 nanometer of titanium, followed by 100 nanometer of platinum, and finished the 500 nanometer of gold layer on a silicon substrate. Now let's look on the good sample on the left. The depth profile clearly shows distinct transition within each metal layer. You can see this both in the spectra and in 3D reconstruction. There the layers are well separated. Now compare that to the bed sample on the right. Even if the optical image we can see, even on the optical image they can see something is wrong, but to understand why they need to analyze it in deep. The depth profile reveals a lot of mixing between layers, especially in the middle region. This is even more obvious in the 3D reconstruction. There are, instead of clean layer boundaries, we see significant interpenetration within metals. The 2D overlays at the bottom tell us even more. In the good sample, we see very little contamination. There are almost no unwanted elements like sodium, calcium, or potassium. But in the bad sample, there is a lot of contamination. Those bright spots on the overlay indicates the presence of these elements. This analysis shows that delamination issues can be directly linked to both structural integrity and contamination in the metal layers. Understanding these failure modes is crucial for improving the deposition process and ensuring quality control. In this experiment, they used ToF-SIMS to track oxygen isotope diffusion in a ceramic material. Let's break it down. On the left, you see the distribution of native oxygen isotope 16. On the right, we have oxygen 18, which was infused through the high temperature time-controlled process. So why ToF-SIMS so powerful for this analysis? Unlike other techniques that only measure total oxygen content, ToF-SIMS can actually distinguish between isotopes. The line scan helps us quantify the colors in the image, showing how oxygen 18 penetrates as a function of distance from the surface. This ability to both image and quantify the distribution of oxygen, 16 and 18 simultaneously, makes ToF-SIMS an essential tool for studying diffusion mechanisms. This experiment is in some way continuous to previous. This is a classic use of isotopes for mechanism investigation and clever use of ToF-SIMS for its measurement. To investigate paint degradation mechanism, the researchers conduct an experiment using O18 labeled oxygen as a tracer. Metal samples coated with paint that are exposed to UV light in an atmosphere containing O18, simulating environmental aging effect. Let's start from understanding the experimental design. Baseline sample was kept at normal condition. A control sample was exposed to O18, but not to UV light, and the test sample was exposed to both UV and O18. After exposure, ToF-SIMS was used to measure the O18 image of the paint cross-section, like on the previous slide. The figures represent a line scan of penetration of O18 with the paint layer. This is for the baseline, they see very low O18 signal. It represents O18 presented in nature. The control sample has clearly higher O18 signal as a result of exposure. However, UV radiation significantly enhances oxygen diffusion, leading to deeper oxidation within the test sample. By distinguishing induced oxidation from naturally occurring oxygen in the samples, this study provides valuable method to investigate durability and failure mechanism for paints, polymers, and coatings. In this part of the presentation, I would like to focus on answering a frequent question about sample preparation, data acquisition, and interpretation. Then discussing sample preparation, we should start from which types of materials can be measured. And the answer is almost everything, from metals through polymers and glass up to powders and biomaterials. The only requirements are it should be solid, stable in ultra-high vacuum conditions, and there are some limitations for sample size. Also, it should be mentioned that for better results, the surface should be as flat as possible. How to handle the samples? The samples should be handled with gloves and packed in glass, hard plastic, or aluminum foil. Let's go to the data acquisition. So, what should we measure, positive or negative ions? In ToF-SIMS analysis, we can operate in either positive or negative ion mode. The efficiency of generating these secondary ions is quantified by ion yield, which is the fraction of sputtered atoms that become ionized. Looking at lithium and sulfur as an example, let's understand that determines the ion yield in positive or negative mode. Lithium, with its low ionization energy of 5.39 electron volt and small electron affinity of 0.69 electron volt, strongly favors positive ion formation. Its electronic properties tell us it readily gives up electrons rather than accept them. This makes it an excellent candidate for detection in positive mode. In contrast, sulfur represents why some elements can be measured only in negative mode. It's a much higher ionization energy of 10.36 electron volt and substantial electron affinity of 2.08 electron volt. Sulfur preferably forms negative ions during the sputtering process. This illustrates a fundamental principle of SIMS. For positive mode, elements with lower ionization potentials, like metals, generally have higher ion yield, while in negative mode, elements with higher electron affinities, like halogens, produce better yield. Which sputter gun to choose? When selecting a sputter gun, there are a few key factors to keep in mind. If you're doing depth profiling for elements measured in positive mode, these are shown in red, oxygen sputtering is best choice. For elements marked in blue, like chlorine, fluorine, cesium sputtering in negative mode gives better results. Some elements like carbon and boron, marked in purple, work well with either oxygen or cesium. The choice depends on specific application. And then working with organic samples, an argon cluster ion beam is the preferred option if you have access to one, of course. Should we measure spectra or image? In physics, we often encounter a situation where the need to balance multiple parameters, and this triangle perfectly illustrates one such a trade-off. At the corners of the triangle, we have 3 parameters of ToF-SIMS. At the top, we have number of ions per shot, which directly affects our acquisition time. On the bottom left, we have focus quality, which determines our lateral resolution. And on the bottom right, we have pulse length, which influences our mass resolution. The key point here is that you can't optimize all 3 simultaneously. Different position in this triangle represents different operational modes, and we need to choose our position based on our specific analytical needs. Looking at the box, here how to decide. If your primary goal is material identification, you will want to prioritize spectra. If you already know your chemistry and need good spatial information, go for imaging. And in the case where you're not certain about the chemistry but still need a good spatial resolution, you will want to first get the spectra, then capture the image. What is the max depth profile? It's a few microns. And what if the sample is insulated? There are a few technical adaptations to work did insulating samples like flat gun and extraction bias. Also, an instrumental settings adjustment like random raster mode and primary current adjustment. How do we know that the equipment is calibrated? We are using silicon wafer to check the mass resolution and perform mass calibration every measurement. Now, let's move to the data interpretation. And obviously, the first question is, can we have quantitative results? Yes, we can quantify the results in SIMS, but there are important requirements to consider. The formula shows that we have to use relative sensitivity factor and compare the element of interest to reference element. Because of very significant influence of the matrix on the ionization properties of the element of interest, to get reliable quantitative data, specific standard is necessary. It must have the same species in the same matrix as the one we want to quantify. Also, the measurement condition must be same for standard and for sample. The good news are that this reference standard can be produced using ion implantation, allowing to create almost any combination of element and matrices. What is the detection limit? Detection limit is the lower signal detectable above the noise. It depends on many parameters, both instrumental and sample related. A few examples presented in this table show how big can be a difference between detection limits for different elements. Can this say something about chemistry? In some cases. For example, if they have oxide, we will see the oxide ions, the mono ions, as well as D or 3 atom ions. However, their relative intensities will be proportional to ionization probability and not a stoichiometric ratio. How to ensure peak assignment? For elements, we would go and check for presence of relevant isotopes, double ions, and oxides. For molecules, the best way will be to check for references. And that brings us to the summary of this talk. As we have seen, ToF-SIMS is a powerful analytical technique with some distinct advantages, but also a few limitations. On the strand side, it is exceptionally surface-sensitive method with incredible trace element sensitivity, down to parts per billion. Unlike many other techniques, it can simultaneously detect all elements, even hydrogen. In static mode, we can analyze samples non-destructively, while depth profiling allows us to create high-resolution 3D visualization when needed. However, it is important to remember the limitations. Quantification isn't straightforward. It requires specific standards. Matrix effect can complicate the interpretation. Depth profiling is destructive to the sample. And while ToF-SIMS excels at elemental analysis, it provides limited chemical bonding information compared to techniques like XPS, for example. Understanding these strengths and limitations is key to using ToF-SIMS effectively. I hope this webinar has helped you appreciate its remarkable capabilities and broad applications, whether in academic research or industrial R&D. Whether you're developing next-generation semiconductor or studying biological materials, ToF-SIMS delivers the molecular-level insights needed to accurate discovery and innovation. With this, I would like to thank you for your attention, and we'll be glad to answer your questions.
Thank you, Tatyana and Lyle, for putting together such an informative overview. We hope the information shared gives you a sense of how much can be done with ToF-SIMS. And before we hop into the Q&A, I do have a few housekeeping notes. Next slide, please. Our speakers did share a ton of information with you today, so if you'd like to reference this presentation later, don't worry, this episode with all the related materials will be available at academy.covalentmetrology.com. Again, we will also be sending the recording directly to the attendees afterwards. If you could use assistance with ToF-SIMS, or if you want to discuss a future potential project, we're also offering free discovery consultations with our covalent experts. You can schedule your appointment through a link that will be sent in the chat now. Next slide, please. One last note before we get started with the Q&A session. You'll see a super quick poll popping up on your screen. If you could help answer these couple questions, it really helps our team connect with you more useful and connect you with more useful, high quality content. And with that, let's get started with the Q&A.
All right, we've got some questions coming in. So I'll start with one about sample preparation and capabilities. So Tatyana, someone's asking, how would you measure powder samples for ToF-SIMS?
We have two different ways to prepare powder sample. You can use a carbon tape, conductive carbon tape, and just stick some amount of powder on it. Or we can create a solution and dry it on silicon wafer and measure this.
Thanks. All right, we'll go on to another question. You mentioned in the talk that mostly the primary ion beam was bismuth. Is there advantages of using different primary ion beams?
For organic samples, when you are interested to measure larger ions, it's better to use larger primary beam. So argon cluster is usually used for these cases. In bismuth primary gun, we also have option to modulate it between single ion bismuth ion or triple ion to improve the resolution for higher masses.
Thanks. Wait, let me look through, see what other questions we have. In your example of the delaminating pads, were you able to get more information on the origin of the contamination from the ToF-SIMS results?
The detected ions, I can remind you that there are sodium, calcium, kalium ions. They are usually representative of the water. So during the process, there are some washing and probably some water drops left on the surface. Then it evaporated, but the contamination from the water remains on the surface.
Thanks. I think we talked a little bit about this in the talk, but I think this is a really good question to probably impacts a lot of people's samples. But can you elaborate a little bit on how we deal with charging on insulating samples, or maybe like how we would identify that the sample is charging in the data, like so we'd know what to look for?
During the measurement, it's immediately visible that sample is charged. The signal become low and peaks are wide. So they usually are using flat gun of electrons to compensate. Also can measure the pulses to allow more charge compensation between the pulses. The other option is to use the bias and compensate again to increase the signal. There are some technical features, I would say, then the measurement performed in scattering mode. So there are many small points, and we can measure them randomly, not one after the other. This also improves, it helps for charge to discharge.
Great, thanks. So another, I think, related question about sample limitations. This question's if you have an uneven surface, what sort of impact does that have on the analysis of your data, or like a rough surface?
Yeah, it's always better to have mirror polished sample. In this case, you have excellent mass resolution, but obviously it's not the real life. It will influence the intensity, it will influence the mass resolution, the peaks will be wider, but there are some post-analysis methods to overcome this. We can work on the results and improve results on, but then we know that the surface was very rough or even a little bit rough.
Thank you. Let's see, look through the questions. This is a question that I think is also really interesting. When you do the depth profiling, you mentioned that there's different options for those ion beams as well. How do you choose which one to use? Is it based on the sample or like the thickness?
Yeah, then we measure some metal sample. We usually will use oxygen. If there is some contamination on the surface, which we also are interested, we will measure twice, once in positive mode and then the cesium in negative mode. Did I answer the question?
I think so. So we have another question here. This is something that we have on some of our techniques. Maybe we can answer for ToF-SIMS about air-free transfer capability, like for example, for battery materials or anything that could be oxidized or reactive with moisture in the air. Is that something we could accommodate with ToF-SIMS, like from a glove box?
Yeah, we can do air-free transfer for ToF-SIMS as well. Yeah.
Yeah, we also at Covalent have that for a few of our other techniques like XPS and XRD. So we can do complementary analysis and take apart batteries in a glove box and handle other air-sensitive materials. Right, another sort of technical question. How do you deal with detector saturation if you have very strong signal from like one species?
Yeah, this is a common problem. Usually we are choosing different ions which represent the same material. For example, if you measure a silicon wafer and the silicon signal is very saturated, we can use silicon 2 or silicon oxide to represent. Silicon oxide is not a very good example in this case, but double ion can be used. Also, there is an option to decrease the primary current, and then we will have less secondary ions. On modern system, usually this problem is less common because of extended sensitivity. But for older system, it happens.
Are there examples of samples where this might be encountered, where like the signal is so strong or you don't have the dynamic range to detect like trace things on those surfaces?
Okay, can you please repeat? I didn't hear you.
I was just wondering if there's examples of materials where we might have like signal saturation or need to be worried about it for certain things.
For the elements which are very sensitive, very intense in SIMS, it's maybe a case. For example, fluorine. It doesn't have any isotopes. And you will have very strong signal of fluorine if it's present in the sample. For lithium, luckily we have isotopes, so when the primary ion is saturated, we can use lithium-6.
Thanks. We have another question about covalent offering modeling capabilities to understand, I guess, like the ionization and sputtering process, particularly through depth profiling to help quantify. I think we can try to answer that.
Yeah, the soft, they have at home soft which allows us to analyze data. It has very strong capabilities. Using relevant references, we can quantify elements even if there are few layers. With different concentration or different elements, we still can have correct representation on the depth profile. I'm not sure what was about simulation because there's not much to simulate in this. But yes, if we speak about depth profiling on a multi-layer system and receiving truthful, not sputter time spectra, it's possible.
Thanks. So we have another question. Talked a little bit about this, but maybe if we don't get other questions, we can answer this. Could you go over some of the best practices for sending samples if people want to send them in? How should we do that? And the best way to package them?
Yeah, so first of all, please use gloves because as we have seen in the first example, our hands are leaving very dominant contamination, and this is the technique is very, very surface sensitive. So we will first see the contamination if it's there, and then the sample. Then if there is option, it's always better to have polished sample if they are speaking about general metal or whatever. The optimal size is 1 by 1 centimeter. This is something that is comfortable to work with, but we also can measure larger and smaller samples. Then you look in how to pack it. Please use hourglass or a hard plastic material, so it will not again contaminate the sample. Aluminum foil is also an option in some cases. So yeah, I think it's all.
All right, I think that about exhausts our questions. So if we don't have any more, we can probably finish up. I'll hand it back to Carissa, and thanks very much, Tatyana, for the Q&A.
Again, thank you all for attending, and we will make sure to send you the recording and slides afterwards. Please check out some other webinars that we have coming up in the future. Thank you all.